morning, students. In today's lecture, we will study some case studies and exercises. We will cover the duality theory, the duality theorems and the complementary slackness conditions. So, let us get started. The first example that we are going to consider is we want to write the dual of the following problem: minimize 6x1 plus 3x2 minus 7x3 subject to 3x1 plus 4x2 plus x3 greater than or equal to 5, 6x1 minus 3x2 plus x3 greater than or equal to 2, and all the variables x1, x2 and x3 greater than or equal to 0. Now, in such type of problems, you have to make sure whether the primal is in the standard form of the primal. So, recall what are the two standard forms of the primal? Either the primal should have minimization of the objective function and the constraints should be of the greater than or equal to type, or the primal should be maximization of the objective function and less than or equal to constraints. Now, in this example, we have the primal of the type minimization with greater than or equal to constraints, and also you recall that the number of the dual variables is equal to the number of the constraints of the primal. Therefore, if we call this as the primal, then the corresponding dual can be written as follows: maximize. Now, how many variables will be there in the dual? There will be 2 variables in the dual and their coefficients will be 5y1 plus 2y2. Why did we get 5? 5 comes from the right hand side of the primal and similarly 2 comes from the right hand side of the second constraint of the primal. Now, we need to write the constraints. The constraints are 3y1 plus 6y2 less than or equal to 6. How did this come? This 3 corresponds to this 3 and this 6 corresponds to this 6, and the right hand side is nothing but the cost coefficient of the first variable of the primal. Similarly, we will write the second constraint, that is 4y1 minus 3y2 less than or equal to 3, and the third constraint will be y1 plus y2 less than or equal to minus 7. Now, do not worry about the negative right hand side, because as far as the writing the dual is concerned, you need not worry if the right hand side is negative. Only when you are going to solve it, then you need to make sure that the right hand side should be greater than or equal to 0. Now, the variables will be y1 and y2 both greater than or equal to 0. Now, you know that the number of variables of the dual is equal to the number of constraints of the primal and vice versa. Also, the minimization of the primal will become the maximization of the dual. Let us look at the second example. The characteristics of this example is that we have an equality sign in the first constraint and the second variable in the primal is unrestricted in sign. Therefore, how do we write the dual for this? If this is the primal, then the dual is as follows: minimization will become maximization, and as you can see there are 3 constraints. So, there will be 3 dual variables y1, y2 and y3. So, what will be those 3 variables? It will be y1 plus 6 y2 plus 4 y3. As you can see that these coefficients have come from the right hand side of the constraints of the primal. Then we will have the constraints as follows: 2 y1 plus 3 y2 plus 17 y3. This should be less than or equal to 48. You can see the transpose of the matrix has been taken, and the right hand side is now the cost coefficient of the primal, and the second constraint becomes 8 y1 plus 4 y2 plus 4 y3. This should be equal to 21. Now, why is this an equality? The reason is that the second constraint of the primal is unrestricted in sign. Also, y1 should be greater than or equal to 0. Sorry, y1 should be unrestricted in sign. Why is that so? Because the first constraint of the primal is an equality, and y2 should be greater than 0 and y3 should be greater than 0. So, that is it. So, we have the dual in terms of 3 variables. So, remember that if you have an equality constraint in the primal, that corresponds to a unrestricted variable in the dual, and similarly if there is an unrestricted variable in the primal, it corresponds to an equality constraint in the dual. So, now let us look at the third example. In this example, we are required to show that the following primal LPP has an unbounded solution, and also the question says what can you say about the solution of its dual using some of the theorems that you have learnt in this section. Also, we are required to verify the results. So, as you can see that this problem is a 2 variable problem, and we can easily solve it to show that this is an unbounded solution. So, let us go about it, how to solve it. So, first of all we will write 3x1 plus 4x2 subject to minus x1 plus x2 less than or equal to 1, x1 plus x2 greater than or equal to 4, and both the variables are greater than or equal to 0. So, for solving it graphically, we need 2 points. It passes through 0, 1 and minus 1, 0, and similarly the second constraint, it has the 2 points 0, 4 and 4, 0. So, let us plot this problem. So, here you are 1, 2, 3, 4, 1, 2, 3, 4, and it should pass through 0, 1 and minus 1, 0. So, this is the first constraint, and as you know that since it is less than, so the feasible region is below the line. Similarly, the second constraint passes through 0 comma 4 and 4 comma 0 and the feasible region is above the line because it is greater than or equal to 4. Therefore, what is the feasible region? The feasible region is shown in this region. This is the feasible region, and let us now try to find out the coordinates. So, the coordinates are as follows: A is this point and its coordinates are given by 3 comma 2, 5 comma 2 and the objective function value is 3x1 plus 4x2, and similarly B is the point 4 comma 0, this is the point B. So, the objective function value is 14.5 and 12. Also, if you take any point P on this line, it will be having coordinates t and t plus 1. So, the point P, which is a generalized point on this line segment, will have a objective function value as, let us say, 74 if you take t is equal to, let us say, 10, because it will be of the type 7t plus 4. This tells us that the problem has an unbounded solution. The feasible region is also unbounded and objective function value is also unbounded. Now, recall the theorems that we had learned. If we write the dual, what should be the solution of the dual? The solution of the dual should be infeasible. Remember the theorem, if primal is unbounded, then dual is infeasible. So, based on this result, we can directly write that the solution of the dual is infeasible. Let us write the dual of this problem. What is the dual? The dual of the problem P is minimize y1 minus 4 y2 subject to minus y1 minus y2 greater than or equal to 3, y1 minus y2 greater than or equal to 4, and y1 and y2 should be greater than or equal to 0. Now, you can easily check that the solution of this problem is infeasible. So, you can verify it graphically or otherwise, and I can leave this as an exercise for you to verify that this problem has an infeasible solution. Next, let us look at the next example, which says that read the solution of the dual from the optimum table of the primal and verify your results. Now, you remember that in this lecture we had written the initial table, the intermediate tables and the final table, and there we found how we can read the solution of the dual from the optimum solution of the primal. So, let us look at this problem. We have to find out first the optimum table, maximize twice x1 plus x2 subject to twice x1 minus x2 less than or equal to 8, x1 plus twice x2 less than equal to 14, minus x1 plus x2 less than or equal to 4, and both x1 and x2 should be greater than or equal to 0. Now, although it is a 2 variable problem, we can solve it graphically, but since we want to find out the solution of the dual from the optimum table of the primal, therefore, we need to solve it using the simplex procedure. So, let us see how we will solve it. So, first of all, we have the problem as follows: maximize twice x1 plus x2 subject to twice x1 minus x2 less than or equal to 8, x1 plus twice x2 less than or equal to 14, minus x1 plus x2 less than or equal to 14, x1 and x2 are both greater than or equal to 0. So, in order to solve this, we need to convert all the inequalities into a equality. So, we will write twice x1 minus x2 plus x3 is equal to 8. Second constraint we will write as x1 plus twice x2 plus x4 is equal to 14, and the third constraint will be minus x1 plus x2 plus x5 is equal to 4, and all of the xi's should be greater than or equal to 0 for I is equal to 1 to up to 5. Now, let us write the calculations in the form of the table. So, as you know, first of all we will write the basis. The basis is x3, x4 and x5, and the variables are x1, x2, x3, x4, x5 and the right hand side. So, the data inside is 2 1 1 minus 1 2 1 1 0 0 0 1 0 0 0 1, and the right hand side is 8 14 and 4. The coefficients of the objective function are 2 1 0 and 0. Of course, the coefficients of the objective function has to be rewritten here, and as you can see that the according to the deviation entry, this 2 is the pivot. These are the deviation entries and accordingly 2 is the pivot. Therefore, the new basis will become x1, x4 and x5, and the entries will become 1 0 0 minus 1 by 2, 5 by 2 and 1 by 2, 1 by 2, minus 1 by 2, 1 by 2, 0 1 0, 0 0 1, and the right hand side will be 4, 10 and 8. Then the deviation entry will be 0 2 minus 1, 0 and 0, and therefore, the new basis will become x1, x2 and x5. Here the entries will be 1 0 0, 0 1 0, 2 by 5, minus 1 by 5, 3 by 5, 1 by 5, 2 by 5, minus 1 by 5, 0 0 1, and the right hand side will be 6 4 and 6. and the deviation entries, by the way I forgot to write this, 2 0 0 and here it will be 2 1 0. So, the deviation entries will be 0 0 minus 3 by 4 minus 4 by 5 and 0. Also the objective function value is 18, and as you can see that this is the optimum, this is the optimum table. Now, coming to the requirement of the question, we need to find out the solution of the dual reading it from the optimum table. So, how do we find it? Actually there are two ways of doing it. What is the first method? First method is look at this basis of the initial table 1 0 0 0 1 0 0 0 1 and its corresponding matrix in the optimum table, right. So, this is nothing but this has to be multiplied by this vector. So, 2 1 0 multiplied by this matrix 2 by 5 minus 1 by 5 3 by 5 1 by 5 2 by 5 and minus 1 by 5 and 0 0 1. Now, if you multiply this, what will you get? You will get 3 by 5, 4 by 5 and 0. Now, this is the first way of getting the solution of the dual. Second method is you just look at the deviation entries over here, sorry this should be 5. If you look at the deviation entries over here, take its negative of the deviation entries corresponding to the inverse matrix starting from the initial table. So, therefore, here again what do we find? We find that the solution is y1 is equal to 3 by 5, y2 is equal to 4 by 5 and y3 is equal to 0, solution of the dual. So, I hope everybody has understood the relationship between the solution of the primal and the solution of the dual. So, the next question is we want to find out if the primal is given to be maximize x1 plus x2 plus x3 subject to twice x1 plus x2 plus twice x3 less than or equal to 2, 4x1 plus 2x2 plus x3 less than or equal to 2, x1 and x2 and x3 are all greater than or equal to 0. First we need to write its dual, and as you can see very well that the dual will be a 2 variable problem. Also we need to solve the dual graphically. This is the A part of the question, and the second part of the question says using the complementary slackness conditions we need to obtain the solution of the primal. Now, as you can see the dual of this problem will be minimization of 2y1 plus 2y2 subject to 2y1 plus 4y2 greater than or equal to 1, y1 plus 2y2 greater than or equal to 1, and the third constraint will be 2y1 plus y2 greater than or equal to 1, y1 and y2 should be both greater than or equal to 0. So, this is the dual, and as you can see it is a 2 variable problem. So, therefore, we can solve it using graphically. So, what is the solution of this problem? So, solution, as I will leave it as an exercise, solution of the primal is as follows. Sorry, solution of the dual is 1 by 3 comma 1 by 3 and the objective function value is 4 by 3. You can do it as an exercise. I am leaving the proof as exercise because you are now quite comfortable in obtaining the solution graphically. Now, what are the two complementary conditions that we will make use over here? So, let us try to look at the two complementary conditions. We will use the following two conditions. Number 1, if the dual variable is positive, then the primal constraint will be satisfied as an equality at the optimum. This is the first complementary slackness condition that we will be using. Second condition that we will be using is if the primal constraint is a strict inequality, that means there is no is equal to, at the optimum then the corresponding dual variable must be 0 at the optimum. And using these two conditions, we can easily see that the solution of the primal is 0 comma 2 by 3 comma 2 by 3 and f is equal to 4 by 3. So, this is another way in which you can use the complementary slackness conditions to obtain the solution of the primal from the solution of the dual. So, with this we come to an end of this lecture where we had studied some case studies and examples based on the duality theory and the duality theorems and the complementary slackness conditions. Thank you.